An MM1Q is operating in steady state, and it has a ratio R of the arrivals rate over the service rate being less than 1. And so it can operate in steady state. And we were asked to show that the steady state customer time for a new customer entering the queue has a lambda s minus lambda a exponential distribution. So the idea to show this is to find and recognize the moment generating function for this steady state customer time. This would first be done by conditioning on the number in the queue when this new customer arrives. So the steady state setup is that the queue is operating in steady state prior to this new customer's arrival. So if T0 is a time at which it's in steady state, the probability of Q of T0 being equal to I is pi I, the steady state distribution of queue size, and that's 1 minus R to the I. So we're going to need that later when we average over the number in the queue. The other part of this setup is that when QT0 is equal to n, so there are n customers in the queue prior to this new customer, then the customer time through the queue would be Tc is equal to T1 plus T2 plus Tn plus Tn plus 1, where T1 through Tn are the times to process the n existing customers and Tn plus 1 is the time to process this new one. Now we know that service is a lambda s Poisson process when the queue is non-empty, and we know it's not empty. Poisson processes have independent inter-arrival times, so we know that T1 up to Tn plus 1 given T0 is equal to n are independent lambda s exponential random variables. And so now we can find this conditional moment generating function. So it's conditioned on there being n customers in the queue when this new customer arrived. And so we find the expected value of e to the tc, that's the customer time, u, given that qt0 is equal to n. Well, tc is just the sum of these t1 plus t2 all the way up to plus Tn plus 1. So we just substitute that in and use properties of the exponential to write it as products. So it's e of et1u, et2u, all the way up to etnu, etn plus 1u, given qt is equal to 0. Then we can use independence to write the expectation of that product as the product of expectations using this conditional independence. And so we have the conditional expected value of e of t1 u given qt0 is equal to n, all the way up to the conditional expected value of e tn plus 1 u given qt is equal to n. And so now we can recall that each of these ti's are lambda s exponentials, and lambda s exponentials have moment generating functions lambda s over lambda s minus u. And that's good for u in absolute value being less than s. So therefore, each expected value of etiu given qt is equal to n is equal to lambda s over lambda s minus u for all u between minus lambda s and lambda s. And so then multiplying out n plus 1 of them and using the above factorization, we have that the expected value of etu given qt0 is equal to n is equal to lambda s over lambda s minus u to the power n plus 1 for u being between minus lambda and lambda. And this is good for all n is equal to 0, 1, 2, 3, etc. And so now we can substitute in the fact that we have set qt0 to be n, and so we find the expected value of etu given qt0 is equal to lambda s over lambda s minus u, all to the qt0 plus 1. Our next goal is to convert this conditional moment generating function into a regular moment generating function. And we do that by total expectation applied to these moment generating functions. So in particular, the expected value of ET or TCU is equal to the expected value of the conditional expectation of ETU given QT0, We have done the inner conditional expectation, and so what's left is that outer expectation, which amounts to taking the expectation of the inner conditional expectation with respect to this Q in steady state. But we found the inner conditional expectation was lambda s over lambda s minus u all to the power qt0 plus 1. And so taking the outer expectation is averaging over the q, i.e. qt0 in steady state. Now since qt0 is the q in steady state, its probability mass function, pi I, is given by 1 minus r to the I, where r is the ratio of lambda a over lambda s. And so taking this expectation is just expectation by PMF, which then amounts to the summation I equals 0 to infinity of lambda s over lambda s minus u to the I plus 1 times 1 minus r to the I. And this then can be simplified to lambda s over lambda s minus u times 1 minus r times the summation I equals 0 to infinity of lambda sr over lambda s minus u to the I. And the summation from I equals 0 to infinity of lambda s r over lambda s minus u to the I is a geometric summation, and we know that's then the first value, which is plug in I equals 0, which causes that to be 1, over 1 minus the step, and the step is what you're multiplying by, which is lambda sr over lambda s minus u. And so this summation then is equal to 1 over 1 minus lambda sr over lambda s minus u, and that simplifies to lambda s minus u over lambda s minus u minus lambda sr. However, lambda sr is just lambda a, and so substituting everything back in, we have that the moment generating function, the expected value of ETU, is equal to lambda s over lambda s minus u times 1 minus r times this expression we just computed, lambda s minus u over lambda s minus lambda a minus u, and that's good for all u in minus lambda s times 1 minus r up to lambda s times 1 minus r. And then we can just simplify by noting that lambda sr is lambda a. And so now we can just recognize what we have. What we have is a moment generating function, which is lambda s minus lambda a over lambda s minus lambda a minus u. And we know lambda s is greater than lambda a. And so this is just the moment generating function of lambda s minus lambda a exponential. This means that our desired random variable t is lambda s minus lambda a exponential with probability density function ft equals lambda s minus lambda a, the exponential of minus lambda s minus lambda a times t.
Dear U of A students, while Mike has supplied the content for these videos, there is significant unpaid effort that goes into producing these videos. The folks here at Step by Step Probability are family people with young children that no longer attend school due to the COVID shutdown. Instead of spending time with our families, we made arrangements to continue producing these videos for you. In these uncertain times, it would be very encouraging to see your support through our donation button at the top of the website. Any amount is encouraging and appreciated. Please donate if you can. Thank you and keep safe.